Okay, good afternoon, everyone. Let's begin. Today we have Dr. Emin Kutay. He is an associate professor at Michigan State University. Before joining MSU, he was a researcher and laboratory manager at the Turner Fairbank Highway Research Center with the FHWA in Washington, D.C. For the past 15 years, Dr. Kutay has published more than 90 peer-reviewed papers, reports, and conference proceedings. His specialty is the modeling of asphalt concrete. So let's please give a warm welcome to Dr. Kutay.
Well, thank you so much. Does this work, by the way? It doesn't sound like. Is it working?
Yes, it is.
Everybody hears me well? Oh, perfect. Excellent. Very good. Well, thank you so much for such a warm welcome. And they've been feeding me all last night and today, and let's see how much I can produce now, and we'll see. So that's been an honor. I've been to this facility only once, I believe. I was very impressed back then when I came here, and I am also, again, I'm always impressed with all the work that UIUC folks are doing here, and it's really an honor to be invited here to talk. The chances are you're not going to learn much, you're going to just watch, and hopefully, maybe I'll learn something from you when you ask a question. We'll see about all that. Now, what I'd like to present today is, of course, as many of you do, we do a lot of work on different areas, and I decided to pick one topic and focus on that one topic. Let's just talk about that one topic, and today's discussion will be on that topic. We can discuss about other work that we have done in the past, offline at then in case you're interested. So the topic I'm going to talk about is the falling weight deflectometer data, and how we can analyze this data to get one of the fundamental material properties of asphalt pavements, namely the dynamic modulus master curve. So we are really very much interested in obtaining the dynamic modulus master curve. One of the questions is, can we get the master curve, dynamic modulus master curve, from the FWD data that we have, and FWDs that we have at the moment. Before I start with the technical content, I'd like to acknowledge a couple of things. One of them is obviously the funding that was provided by the Federal Highway Administration. So we have a final report on this. The main person, my student, Sudhir Varma, who did most of the work here. So what I'm presenting is all his work. So that's what we do. Professors, really students do the work and take all the credit, right? That's what I'm doing today. So no offense to anybody. So Siva, obviously, Siva was the COTR on this project. So his work, his comments are greatly appreciated, and obviously my co-PI, he was the PI of this particular project, Dr. Karim Chatti. All the work that he has done obviously is appreciated. So now a little bit of an introduction. I assume you all know what dynamic modulus is and dynamic modulus master curve is. And we know that dynamic modulus is a very key input to many softwares. Emin is one of them. MIPA is a software like PaymentMe, CalMe, FlexPay. There are many other software. If you do finite element analysis, you need dynamic modulus master curve as well. So it's an important parameter. So now one of the things is, can we get the in-situ dynamic modulus from the field? That's one of the things that we are interested in. Of course, we can run the laboratory tests to get this parameter, but that is the main idea of this particular work. Now, the problem statement was formulated in a way that can the current FWD systems, is there any way that we can use these systems to get the dynamic modulus master curve? They are not designed to get the dynamic modulus master curve. So originally when they were designed, Dr. Thompson was showing me very early designs of FWD. You have a weight, you drop it, and then deflections. I don't think it was designed for the dynamic modulus back then. I assume So later on, obviously, it has been improved quite a bit. Now, the chances are, at the time when we were starting this work, chances are it is not sufficient. It's not enough to get the dynamic modulus. So if it is not enough, what is it needed to improve the FWD so that we can get the dynamic modulus master curve? So early on, we were entertaining the ideas of, okay, multiple pulses. Can we come up with equipment with multiple pulses and get the data properly? And, you know, can we get the dynamic modulus that way? So this is just an early on discussions and all that. So, you know, a little bit of spoiler alert at the very end, and I'll be telling you that if the dynamic module, if the FWD data time history is collected properly by the equipment, and if the temperatures are known in the pavement or at multiple temperatures you run the FWD, you should be able to get the dynamic modulus master curve pretty good with the existing devices. So that's the spoiler alert. But you know, I'll tell you about all, you know, how we get to that conclusion. Okay. Now, pavement ME, as I said, it's very important that dynamic modulus master curve. Oops, I pressed the same thing. I think these buttons are pretty close to each other. So in pavement ME, what I was showing here, this is just a snapshot of the pavement ME, all the different components of the pavement ME or MPG, and dynamic modulus. Modules at different temperatures, at different loading speeds are they are heavily utilized in pavement ME. And that dynamic modulus, if you look at the NCHRP 147 study, sensitivity study, they have these what they call tornado plots. In these tornado plots, they look like a tornado like this. And if you look at this very top, so this is kind of sorted in a way that the highly sensitive parameters are at the top and low sensitive parameters are at the bottom. And the numbers, what you are seeing here is first two are hot mix asphalt alpha parameter, which is essentially this parameter. You probably know all this. Dynamic modulus can be represented using a sigmoid. So this alpha parameter and delta parameter, they are the two most sensitive parameters to in MEPDG. So the outputs are very sensitive to these two. So it's important to get these two, even more so than the thickness in this graph shows. So we all understand dynamic modulus. It's important. It's a parameter that we want to get. So first we need to be convinced of that, obviously, right? Now, how we get that? So now we're going to come up with, we develop a bunch of algorithms so that we can simulate falling weight deflectometer stress and the output strain. Now, one of the things we did is we call them forward algorithms. So we developed layered viscoelastic, multi-layered viscoelastic forward algorithms. So now if you look at the linear viscoelastic system for a uniaxial sample, now I'll try to talk, I will actually provide some equations on the screen. You just ate, right? I assume your brains are working perfectly. So I know that it's dangerous to show equations on the screen while you're presenting. I know all that, but I will do it regardless, okay? So, but I hope most of you enjoy this. So you know the convolution integral to get the strain versus time from a stress versus time history. So you need the creep compliance master curve. So you get the creep compliance master curve for a uniaxial system. You have the stress history. You can do the convolution to get the strain history. So in here, what we have is this is something very well known. So what we have is the unit response function, which is the D of T. So response to a unit load. Now, in a system like a multi-layered axisymmetric system, we can use something similar, a concept similar. So what you're seeing here is, if we have the unit response, R is the response, H is the unit for unit, R, HVE. If we have the unit response, this response could be deflections, stresses, strains, anything. If we have the response, unit response in this system, we can do the convolution to come up with the viscoelastic response. So we have shown that this is true in FWD through the finite element analysis, and you will see this. It's somewhat similar to a uniaxial system. Now, in this case, in this particular problem, FWD deflections are of interest. So the response that we are talking about here is the U, and U in here is the vertical deflections. That's the only one that I'll be discussing throughout, not the stresses or inside stresses or strains in this talk. So I'm replacing RVE, which is UV, EU being the deflections at different locations. So, and this 0, Z is equal to 0. So we are only interested in surface deflections because we are only looking at the FWD data. Now, one of the most important key aspects of this overall thing is how to get this unit response deflections, viscoelastic unit deflections. Shapery showed that we can use this convolution. Let's see. We can use convolution to get the viscoelastic deflections or viscoelastic response if we use the unit response due to an elastic analysis evaluated at relaxation modulus at that particular time t. In other words, so instead of running a full-blown viscoelastic unit response, if you actually do a layered elastic analysis using a unit load, however, for different times, you evaluate different, you run the layered elastic analysis using the modulus at different times. So when you do that, then what we call unit response master curves are generated. So for the very first step here in this whole analysis, we generate the unit response master curves. So these are essentially just like T of T. Think of this as a creep compliance master curve. Of course, it has a very different shape. So it's like a unit response master curve. So this blue line, what you're seeing is the deflection right at the middle sensor. The green line is deflection at 8 inches from the center. So as you can see, with time, reduced time, the sensitivity to the reduced time decreases as we get away from the center lobe, which is very logical. So these are your unit responses, and we plug them in here to come up with the viscoelastic response. Now, how about the effect of temperature? Now, effect of temperature is obviously very important. So far, I haven't talked about the temperature. So we know that asphalt mixtures, they obey the time temperature superposition principle. So we can use the shift factors to use the temperature with depth. So what this is showing you, this is actually a typical simulation of temperature. This is really coming from the MIPA software, but it's essentially the same model that's developed by Dr. Barry Dempsey right here in this institution. It's just literally all his thesis is implemented in this code. It's the EICM code, the same thing. You can see the temperatures vary very widely. So this is a good thing for us. If you are interested in getting the dynamic modulus master curve, fluctuation of temperature is a very good thing because you want to get that information. If you have that information, you can get the shift factor coefficients also, not just the dynamic modulus. And this is just a slide that shows how we got that temperature versus depth. Essentially, again, the Barry Dempsey's model based on 1969 thesis that he has. Anyway, so bottom line is we would like to be able to exploit this information. Sometimes asphalt concrete has a temperature, like this is the daytime temperature kind of a thing. So you have a variation, and sometimes at certain times of the day, it's pretty much constant. So we need to know all this. Now, if the pavement temperature is constant, so things are easier. So instead of time here, we use the reduced time. So we use essentially the time divided by the shift factor coefficients. Essentially, instead of the modulus at certain time, we use at reduced time to find the same, to perform the same convolution. So to recap, a little more step-by-step description on how we do all this. Certain things that I'll be repeating a couple of times on purpose, hopefully, to convey what I'm trying to say a little bit better.
So the step one is obviously the coming up with the structure and what kind of structure that you have. Step two is come up with a trial or whatever the input relaxation modulus master curve. So if you know the dynamic modulus master curve, you can calculate mathematically the relaxation modulus master curve. I assume you know all this through Prony series or some other methods. So in the forward algorithm, we have the dynamic modulus master curve, and we calculate the relaxation modulus master curve at the reference temperature of 19 degrees Celsius, for example, in this particular case. Now what we do is for a given time and for a given temperature, we look at the modulus that corresponds to this particular time, and then we plug that modulus into the in the layered elastic analysis, and then we come up with this what I just said, a unit response master curve. This particular point is just this point, and we repeat this for all different times throughout the essentially the relaxation modulus master curve. All these little dots that results in this one, and then once this is done, this is your unit response master curve. Then now this is your stress response right here. Transient stress response, FWD response, this is simulated here. So essentially, viscoelastic deflections at different locations are simply taking this data from here, for example. This data is the relaxation unit response master curve for a sensor R is equal to 0, and combined with the stress here to come up with the viscoelastic deflections. So when we have temperature profile, things are almost exactly the same. It's not different, except for different temperatures, we sublayer this AC layer into multiple sublayers as fine as you want. It depends on how accurate you want. For each sublayer, you have different temperatures. For each sublayer, you go to the relaxation modulus master curve, find your reduced time, and then place the modulus based on the reduced time. Again, generate a set of unit response master curves, and then combine that with the stress to come up with the viscoelastic deflection. So when you have temperature profile versus single temperature, the algorithm is identical. There's no difference. Obviously, your layered elastic code needs to work really well. That's one thing. Now, obviously we have to validate whether this works, the whole idea works or not. So, we did that many times. What I'm showing you is one of them using Abacus. I have some other slides that we compared against dynamic viscoelastic solutions like SAPSI and Lambda, but I'm just showing Abacus. This is the Abacus world, right, Emin? This place.
Yeah.
We use a lot of Abacus, so that's why it's designed. So these are the deflections calculated by Abacus viscoelastic, and these are what we call lava P. Lava is layered viscoelastic. The name of the algorithm that we have, layered viscoelastic analysis. P is for temperature profile. So there's a reason why we come up with the forward algorithm to be lava, and you'll hear that has something to do with me being Turkish originally. So you'll learn about this a little bit later. Hassan is looking at me like, what? I don't get it. So you'll understand in few slides, okay? So anyway, so I'm going to move into lava N. Lava N is layered viscoelastic analysis nonlinear. So we know that unbound materials are nonlinear materials. This is just an simpler representation of nonlinear materials. Sugars, if you put confinement, obviously it can stand much better. You can have a larger modulus when you have confinement. Unbound materials are something like that. Now, can we include the nonlinearity of unbound materials in the layered elastic analysis? The immediate answer is obviously not. No. The immediate answer is no. Why? Well, nonlinearity, layered elastic analysis are all based on a single modulus constant being in radial direction, right? So if you have stress changing in radial direction, and you're going to have stress states changing in radial direction, and that's going to influence the modulus in radial direction. So the obvious answer, accurate answer is no. Answer is no. You can't do that. How about, can we do this indirectly, approximately? The answer is possibly. Okay? So now what I'm going to describe here is, we are interested in getting the nonlinear properties of the base layer also by doing some tricks, if possible. If possible. So that's what we did. So now, one thing that we wanted to do is, so again, a little bit of a spoiler alert. Can we use the stress state either at the center or a little bit far away from the center? Would that be representative of the stress state for the whole thing? So can we use like an average modulus based on the stress state in there? So that was the main question. So the answer was yes. But one problem here is when the whole thing becomes nonlinear and viscoelastic, things become pretty complicated. Now, how do we solve for this? So, can we use the traditional nonlinear viscoelastic solution? So there are traditional nonlinear viscoelastic solutions like quasi-linear viscoelasticity. There's shape-breeze nonlinearity. So these are some of the methods. So I'll be working on this. We tried all these. And that's what I will be talking about a little bit. Let's talk about the trial of quasi-linear viscoelasticity. So now in the quasi-linear viscoelasticity, you have the d of t, now not just a function of time or temperature, and also a function of the stress. This is for a uniaxial case. We started from a uniaxial case, and see we can move to a multi-layered elastic analysis. Now, in the quasi-linear viscoelasticity, usually the idea is can we divide this into two components? One of them is only based on function of time, and it's independent of stress, and it represents the shape of the creep function. So if you look at d sub t, that's what this one. And the second one is g sigma. G sigma is the component that is only of a function of the stress, not dependent on time. Okay, so that's what quasi-linear viscoelasticity is. So can we divide this into this? That was our trial. And if we can, then we can separate these two. And then if indeed this is independent of time, this can go outside the convolution, so things become a bit easy. Now, when we try to do this, first thing we wanted to look is whether this is true or not. Whether this G sigma first of all, is there a G sigma that is independent of time? So for that to work, so if this is G sigma, now I'm rewriting the equation in terms of the unit response deflections. So instead of d of t, I'm writing u e h t. So for this to work, this divided by this should be constant, independent of the time. So that means that for different stress states, all these needs to collapse on a single curve. So when we did this, we did a lot of calculations of viscoelastic deflections and many different unit response, so these are all forward analyses that we have done. The answer was no. The answer was no. So there is no such thing as G sigma in a multi-layered condition. So this complicates things. So this quasi-linear viscoelasticity did not work essentially. So this is a slightly different way of showing the same data here. Some like surfaces, some like graphs like these. So this is the same kind of a data. G sigma as a function of relaxation modulus at different stress states. So if the G sigma to be a unique number, it should be a single constant number. Okay? So it didn't work. Now, then how do we do this? Should we give up or should we find a different way? So what we did is we decided to, okay, can we use this entire curve as a, like a lookup table? So we generate this matrix of different sigmas and different times or different moduli values. What are the these unit response functions. So now unit response function is not a single line, it's a surface. Depending on the stress, it changes. So the convolution can still be done by essentially traveling over the surface. Instead of traveling along the line, you are traveling on the surface to calculate the deflection time. So in order to validate this, things were a little bit more difficult. We had to come up with a UMAT. Not me, my student, Sudhir. Here I wrote a UMAT algorithm in Abacus to implement the nonlinearity of the base in Abacus, and we compared Abacus results versus this approach and see if it works or not. And we tried different mixtures. So asphalt layer is linear viscoelastic. So when I say nonlinear viscoelastic, by the way, let me make it clear again. Asphalt layer is assumed linear viscoelastic. Base layer is assumed nonlinear elastic. So combination is, that's why I'm saying nonlinear viscoelastic. Now, we also looked at many things. So what would be the stress state? Stress state at the center, or stress state at certain far away from, at certain distance from the horizontal should be used to calculate the deflections. So we tried many things, and at the very end we found that if we use the stress about 3.5 times the radius of the FWD load or the surface load, the stress that here would represent the stress state for the whole condition. These are the results. So what you're seeing here is, this is for one type of mix, a stiff mixture used on the top layer. Here what you use is the softer mixture used on the bottom right layer. So the lines are AS means Abacus sensor 1, the first deflection, second and third, and goes like this. LS is the lava N. L stands for lava N software. So these are other deflections and all that. So deflections match reasonably well closer to the sensor, and when it goes further to further, sensors deflections start to deviate from each other. So the bottom line, if we can use the sensors closer to the load center, then we should be able to back calculate nonlinear properties in a reasonable accuracy. Okay. Now, back calculation approach. Now, the back calculation is essentially nothing but running the forward analysis, either lava or lava N or lava P, whatever the algorithm is using, many times, and by varying inputs. Obviously, that's what the back calculation is all about. And one thing that I want to say is, now, if this duration is extremely important. Now, this is a typical FWD duration, 35 milliseconds, very, very short, very short. So let's say going from here to here, let's say this is your time history ends. So whatever this duration is, and if you take the, let's say, reduced time and look at the E of t curve, this is the portion that you are using in your forward analysis. So if this is the reduced time, this up until this point you're using to calculate the deflection time histories of this entire thing. That means that this portion is not utilized during the forward analysis. If you are after calculating this side also, if you're not using the forward, you can't possibly get it. Okay? So that means that one of the biggest issues with FWD is the duration of the pulse. It's very short. So duration of the pulse, that was one of the conclusions, needs to be longer, or the temperatures should be a little bit higher, so that we can use as much as most of the curve as much as possible. That's one of the key recommendations to the FWD manufacturers, is the pulse duration should be a bit long. And one of the things, another big another big advice is really getting the deflection time history very well, which is many of the times the problem, which I'll get there later. Now, when we do the back calculation, so we can either run the FWD, if you know the temperature to be relatively constant, let's say you are in somewhere 4 a.m. in the morning or early in the morning, where the temperature is somewhat comes to that level, and then you can run at multiple temperatures. If you run the FWD at multiple temperatures and get the get the deflection time histories at different temperatures, you can get a bunch of E of t curves, and you can shift them, and you can come up with both shift factor coefficients and the dynamic modulus master curve. Now, do you understand why the lava was chosen? Okay. Back calculation. So, lava. So again, these are another example. So this is a this typical constant temperature profile. This is a typical temperature profile that could be used. So if you have this kind of a temperature, things are harder. You need to run the test at multiple temperatures. Now, if you have a good temperature profile, when I say good temperature profile, pretty large difference throughout the depth. So that's wonderful. That way you can just actually run a single FWD if you know the temperature profile, and then you should be able to get the master curve reasonably well. So these are the algorithms that we have, lava forward algorithms and baklava algorithms. That is the picture of good baklava. Okay. So now the whole issue is an optimization problem. Now from now on, I'll just switch gears a little bit. Now from now on, up until now, I've been discussing, okay, what is mathematically, can we do a forward algorithm? So now what I'd like to come to is the back calculation algorithm. So that is a very challenging problem. So you can have the best forward algorithm, but if your back calculation algorithm is not working very well, it will go to local minima, which will give you weird results, like Bayes modulus being larger than the subgrade modulus, which we see all the time in many of the back calculation algorithms. So you have to be careful. Now, so if you're assuming that if you're assuming the Bayes to be a linear elastic material, we will need 6 unknowns of the AC layer. 4 of them are the force sigmoid coefficients, and 2 are the shift vector coefficients. So we want to get dynamic modulus master curve. So we have 6 unknowns, 1 unknown for the Bayes and 1 unknown for subgrade. So number of unknowns is 8 for a 3-layer structure. Obviously, if you have 4-layer structure, 5-layer structure, if you have multiple AC layers, things can go exponentially complicated. If you have a nonlinear, if you are assuming the Bayes there to be nonlinear, obviously you have K1, K2, and K3. That's the model that we have been using. So you have 3 unknowns here, 6 unknowns and 1 unknown here. Number of unknowns for a 3-layer structure is 10. So this is a pretty large number of unknowns. 8 and 10 is there, both large number of unknowns. So your back calculation or optimization algorithm needs to work really well. So there are many out there. So one of them is, obviously you are all aware of the solver, Excel solver, right? So you can do Excel solver. That's a very simple, simplex algorithm, one of the simplest ones, but that algorithm depends very highly on whatever the input is, and it will go to the local minima very quickly. Global minima is usually hard to get. And if you're using MATLAB, FBin search is another one. Now what we worked on is something called genetic algorithm. So genetic algorithm is essentially, it's a non-traditional optimization algorithm. I can spend half an hour explaining all this, but I won't do that. So essentially what this does, genetic algorithm does, is it has a fancy name, but it's not that fancy. There's no genes involved. It looks like a gene. You have a bunch of inputs. You come to you run the lava, let's say, and then you come to a solution by running multiple times. So you essentially rerun it again by just changing the inputs again. You don't just stop there. So you keep changing in a smart way. That's why it's called this gene. So you're changing the inputs that are in there in a certain way, such that the global solution is reached. So now I'll talk about it a bit more a little bit later. So what we do is, again, the general steps of the back calculation is you have temperature profile, and that is assumed to be known. Thickness is assumed to be known. This is a big assumption. Thickness is assumed to be known. Okay, so you need to get a good thickness statement. So the thickness, we did some sensitivity analysis about, you know, what if we don't know the thickness very well, and if there's an error in thickness, how much everything is affected. The report includes, the FHW report includes all that sensitivity. But this is an important thing that needs to be measured properly. Poisson's ratio, what is the Poisson's ratio? That's also important. There are relationships between modulus and Poisson's ratio that could be used in there. So unknowns are the sigmoid coefficients, C1, C2, C3, and C4. What are these numbers? I have relabeled them. This is alpha, beta, gamma, and delta parameters that I showed earlier, but we like to use these better than the other ones. So A of T coefficient, which is the shift factor coefficients, and unbound layer moduli. These are the unknowns. Now, in the genetic algorithm, we need to know the limits. So that the search has a certain bounds. So what we did is we looked at, we had a database of dynamic modulus master curve that we had developed on hundreds of mixes throughout the years. And these dynamic modulus, we converted them all to E of T curves, relaxation modulus master curves. And then we looked at these C1, C2, C3, and C4. And we tried to come up with a bound, different bounds for C1, C2, C3, and C4. And we used in here, the same here, these are the shift factor coefficients of the dynamic modulus. Let's move on. For the unbound layer properties, we also need some kind of a bound so that our algorithms are fast. So what we did is, for the unbound materials, our idea was, let's just use the traditional simple layered elastic back calculation based on deflections. Let's just take that as a seed and just go plus minus 20-30% of whatever the elastic is. So that would be our unbound. So it's not a wild, search. It's just a little bit, narrowed search so that the optimization worked a little bit better. So this is just an example of this local minima versus global minima. So what happens in simplex algorithms? So this is objective function is essentially the minimization of the deflections relative to the maximum. So oftentimes there are multiple minima that the simplex algorithms can go. So what the genetic algorithm does is it finds a solution and then spreads the solution. Finds the solution, spreads the solution, and until most of the solutions direct to the same location. So that's the idea. So find the solution, spread it again, until most of the solutions are at the global minima, and that's how you get the solution. Here's another example, a couple of examples using synthetic data. So first thing we did is, okay, let's see synthetically, if you know exactly what the deflection is going to be by generation of FWD synthetic data, let's see if we can get those numbers. So this is a simulation of multi-layered structure with about 10 degrees Celsius difference from top to bottom. And so using synthetic data, we were able to get a perfect match. So this genetic algorithm back calculation, we were able to get a perfect match. So this is just really a testing of the algorithm itself, whether if you have a perfect FWD data, would it work? So in this case, this is really like a self-check. It was working very well, so algorithm worked well. So how about in real data, obviously, right? In real data, what we did is we looked into LTPP. So good thing about LTPP database is they have FWD time history. They have also viscoelastic properties of different sections. So we just need to find the good sections with the accurate data. So these are some examples that I'm going to be providing. This is section 0.101, 35, 0801. So these are different field sections. So from the LTPP database, we also had the temperature profiles for these sections during when the FWD test was done. So that data was available. So when the FWD test was done, this was the temperature profile. So top layer was about 38 degrees Celsius, bottom was 33 in this one. And this one is about, top layer was 23, bottom was 17. Here's the results for the section 101. This is the FWD pulse, actual pulse. And these are the deflections. This is Dynatest data, I believe. Those of you who are familiar with FWD data, and then there's a double pulse, it's usually Dynatest data. There are other manufacturers. So we have different drops. Typically, there are multiple drops that are dropped and at different load levels. So this is the dynamic modulus master curve that was actually reported in LTDB database, and this is what the genetic algorithm and simplex algorithm together calculated. And this is the phase angle. Phase angle is doing really well at high reduced frequencies, but at lower, it's really not doing very well. So it's not super accurate at very high reduced frequencies. It is what it is, essentially. Now, this is another section. So these are back calculated results. Sometimes based on different drops would give inconsistent results. So this is one of the issues with FWT is data acquisition needs to be improved. Some of the FWTs, the data acquisition, again, they are not designed to come up with time histories, so the deflection histories are sometimes problematic. Even sometimes you saw pavements growing, deflection histories of pavements growing after the FWT test, which can't happen. So we felt that okay, so this overall approach is promising. So FWD can be used to back calculate dynamic modulus master curve. One, provided that you have good deflection time history measured. Number two, if the temperatures are known, the temperature with depth, which can also be simulated, by the way, but I won't get in there right now. So now we also did some sensitivity analyses. So one of the questions is, okay, what temperatures to run, right? FWD, what is the best temperatures? Which sensors to use? And those kind of things that we discussed and we looked into. And what we did is, what we found is error in unbound modulus decreases when we incorporate more sensors. This is not something surprising. Obviously, if you use further sensors, you can get more information about those lower layers. And error in U of T increases as the more sensors are used. So it's the opposite. So if you are really more interested in the dynamic modulus, you need to use closer sensors. If you're more interested in the base and subbase, you need to use all sensors. It all depends on what you want to do. So what is the optimal temperature set? So we found that these are all simulations using many different temperatures. If the FWD testing is run around this region, anywhere between 10 degrees Celsius to up to 50 degrees Celsius, around this region, that's where the most you can get the most out of it. Okay, so at very low and higher, it doesn't work because at very low temperatures, you're only using this side of the curve. At very high temperatures, you're jumping from here to here too much without using this much properly. So there's a linear jump. So that's really the main point. And we repeated this in many different mixtures, many different dynamic modulus master curves, and they were all consistent. So temperatures around here, 10 to 20 degrees Celsius around this one. Essentially, if the FWD test run at early morning or around noon would be the best case. Now, finally, what I'd like to do is in order to improve the back calculation algorithm, so we came up with a three-stage scheme on calculating the back all possible parameters. First stage is a nonlinear elastic back calculation to come up with the K1, K2, K3 values of the base and subgrade, and a viscoelastic. Then we fix the K1, K2, K3, then vary the viscoelastic dynamic modulus master curve coefficients by fixing the others. And then once we find some initial values, don't use genetic algorithm, but this time, since our seed values are very close to the global solution, we use the simplex algorithm to find, by varying all the parameters. This three-stage scheme turned out to be very fast and pretty accurate also. So these are some of the results. The percentage error between the dynamic moduli at different temperatures are less than 10% or so, which is pretty good,
Considering the dynamic modulus test itself has a 30%
error when you run the test at high temperatures. These are some other examples using the 3-stage algorithm, some back calculation results. Again, another LTPP, nonlinear back calculation results. They have been doing really well. Finally, one last or a couple of last slides about how do you use this data? So can we use this data on LTPP? So what we did is we looked at, we were interested in evolution of E star with time. Can we correlate or can we see any difference cracking observed in the field versus the evolution of dynamic modulus in the field? So we were able to find some LTPP sections with good cracking data and also FWD data at different years. So we found that and we used that data to back calculate. So we were able to see, so initially, obviously increase is captured, like aging. Aging seemed to be captured in some temperatures, and as the cracking grows, reduction in modulus is somewhat captured. It's not always consistent here. Continuous aging seemed to be, that's what we saw in the data. Dealing with the field data is sometimes difficult. So what you're seeing here is, this is a section where there was absolutely no cracking that happened, and dynamic modulus didn't change. So this is another section with, up until here, we had the dynamic modulus increasing a little bit and then decreasing after the damage starting to appear in here. So the data is not super clear, but you can kind of see results there. In conclusion, so again, FWD data is, we can use the FWD data to back calculate the proper dynamic modulus master curve. There are two big ifs. If you have the temperature profile properly calculated or measured. Number two, the sensor deflection time history is accurately measured. That second number two is one of the biggest issues with the current FWDs that needs to be improved. Number three, deflection, the duration of the pulse needs to be increased. So right now it's a very big pulse, and that pulse is also generating dynamics. When you have a bedrock close to the surface, there is wave propagation happening, and because of that wave propagation, you have dynamic effects generated. And these dynamic effects are not necessarily there when a regular truck passes by. So that dynamic effect needs to be removed somehow from the FWDs. So that's one of the things. So I guess that's all that I'd like to discuss. I already said what the conclusions are. So I think that's all for today. Am I good in time or 50 minutes? That's about what I planned.
Any questions for Dr. Kutay?
Thank you for the presentation. It was very good understanding. So, Professor, I was curious about the use of having master curve for the insurance payment. Could you explain that we may use it for payment? And now, as you know, we are using the master curve from the specimen. We assume that it's represented undamaged payment materials. Now we have the master curve that are coming from the payment that has micro cracks and all this somewhat damaged. So can you elaborate on the use of such master curve on MFG and how it will affect the entire calibration process? And second, in general, can you tell us how we can use this master curve?
Yeah, good, very good questions. In Emin EMEA software, you need to know the damage master curve for rehab design. So this is one of the things that is, so if you want to do rehabilitation on an existing road with a certain, so that is one of the things that you need to know. So that is one of the uses. You don't have to use MFPG, obviously. There are other software, you can use your own software if you want. But the bottom line is knowing the existing dynamic modulus, in situ modulus is important. So there are many reasons. Obviously, one of the reasons would be you would run a laboratory test. Of course, if you take a core and take it to the lab and run, that's one. It's just that, sometimes you don't want to do it, but equipment you need. So this is just another way of getting the dynamic modulus master curve. So remaining service life issues we can use like these softwares. Calmi is another software that you can use. If you also, for forensic analyses, for example, you can use this. So dynamic modulus master curve would be a good indicator of the existing condition. So let's say there was the original dynamic modulus that would run on the mixture that was designed. In situ dynamic modulus, let's say it's completely different. Maybe there's an issue with the construction. Construction issues can be resolved. There are many others that can be resolved. It is an important part.
Just a follow-up question. So, because having a lot of cracks on the paper, parting cracks and all that, does it create any kind of implications on the paper?
So if there are a lot of cracks,
yeah.
I don't think you can use it. The whole idea is layered elastic continuum media. So how discontinuous your cracks are. So if you have, if it's completely gone, the pavement is completely damaged, it's a different story. I don't think it's might apply very well. But if it's slightly damaged or damaged to a certain extent, where the overall continuum is not affected too much, then you should.
Is there any specific threshold to define the continuity of the paper? If the crack is less than this much or something, then you can use it.
I don't think they have a threshold.
Thank you for this nice presentation. My question is, at the end, when we do the FWD and then we
Louder, I can't hear.
yeah, so when we do the FWD and then we back calculate the dynamic modulus, so in case it's aged, how do you think that, because we will have like a gradient, right? As for the modulus, so how can we check this gradient?
Very good, very good. So, see, that aging, first of all, it's there. It's very clear. I mean, when you looked at, then we back calculated dynamic modulus at different times from the data. So this increase, it was pretty clear. You can see in several sections, not everywhere, but so when you were asking, what if multiple sublayers, right? So if you have top layer is aging a little more than the others.
Exactly. So there is a gradient, not the aging.
Yeah. So what you will see is, think about one thing is all these. Let me go back to this. Let me see. Okay, come on. Hurry up. Okay, let's talk about this one then. So since the algorithm's sublayer, so it's an input is how many you want to sublayer. Let's say you have a 6-inch layer, you're sublayering into 2-inch layers, 3-inch layers. When you back calculate, you're going to get 6 dynamic modulus coefficients for the top layer, 6 for the middle layer, 6 for the bottom layer. So you're going to get a lot of layers. So you're going to be getting dynamic modulus master curve of each layer separately. So you can see this is that's another uses. So if you get the really good data, say, assuming again, this is a big assumption. Assuming you have a good FW data, test is run properly, deflection time histories are good, and your temperature profile is known, then this shows that you can get dynamic modulus at different layers, non-destructively, which is a very powerful thing to do. You can study aging in this way, or air void effects and all other things. Yes?
What if, like, within the layer there is a aging period? Then in that case it will be averaged, right?
It will be averaged.
So it will be
Yeah.
averaged.
Yes. From the layer will be averaged.
So can us further sub-layer the layers like
Yeah.
everything is done?
You can sub-layers as many layers as you want.
So,
The problem is this, optimization algorithms. So remember 10 unknowns, right? So if you sub-layer into 3, the 10 unknowns becomes 20-something unknowns. So the genetic algorithm, it will take a lot more time to back calculate. For research purposes, which is perfectly fine. You can just let it run, come overnight, come back to results, You can sub-layer as many. For practical people, usually that's not acceptable. But theoretically, yeah, you can sub-layer. I want to give a quick. I haven't tried it. I haven't tried into like 10 different sub-layers and see if it can back calculate. And sublayers. So algorithms are all available for you to research all that. So you can do it if you want. So write it. Yes?
Did you consider the relationship between the frequency when you run a dynamic modulus in the lab and the pulse when you are applying the
So
because when you run the complex modulus, you are applying a frequency, which is a function of y. When you are applying the FWD, it's just a pulse, which is an impact load. So the frequency that you're getting for both are different. So is that was something you looked at?
it is included because
Okay.
we don't use dynamic modules. We use the relaxation modules.
Okay.
So we convert the dynamic modules to relaxation modules. So we are moving from frequency space to time space.
Okay.
So the pulse, the duration, we never use frequency. So we use the entire time history. We use convolution. Therefore, the frequency we never use the background efficiency.
Even the time, wouldn't that be the time impacted in this case? I'm getting back to the point because you said that we need to increase the time for the FWD. I mean,
So the more time you include, the more number of frequencies, in a sense, you're including in the dynamic modules. Because the time, it's not like 1 over t or 1 over f. None of those apply here. So the more time you have, so let's see.
it doesn't apply here, but it does apply to the models that you're measuring in the lab.
So here,
That's true.
so here, this is the relaxation modulus master curve. Once you have this curve, you can calculate directly mathematically dynamic modulus at different frequencies at different temperatures. So all you're trying to do is the larger the component, the portion that you can calculate, the larger the portion of the dynamic modulus frequency space that you can calculate. So it's so here it's not. If you notice, I never use like okay, this is f, this is 1 over f, 1 over t. Because it doesn't apply here because everything is in time space. Everything is time space. We are doing convolution time space. That's the power of this. There are like SAP, C, lambda. There are many dynamic viscoelastic solutions out there. The main problem is how do you characterize this into frequency space? What is the frequency? What is the dominant frequency? There's no dominant frequency. If you take the Fourier transform, comes back to your question. If you take the Fourier transform of this, you'll see multiple peaks.
That's what I noticed because you look into the pairs that you have that are function of the depth, right?
These are actual different sensors.
The different sensors.
Deflections at different locations.
Right, and the different locations is representing different depth, indirectly.
Indirectly,
Yes,
that's true. Indirectly.
Which I'm getting to is the pulse width, would it be different because you have the ball now having the same pulse depth, but you have the amplitude? You see my point where I'm going?
Like the duration?
Yes,
could
the
be-
duration will be different for each sensor as
So-
you are picking the pulse.
So if the sensor was here,
Yeah.
yes. But if it's at the surface, no. Because it's at the surface. It is the sensor itself is indirectly related to depth, but not directly. So it's not duration. The durations are roughly the same. Even if you do a dynamic or dynamic solution, the durations are not going to change. It's not like the pulse duration with depth. Because you go deeper, of course,
Yeah,
they
yeah.
very significant.
Yeah.
You're looking at the surface, usually don't change.
They don't change.
And this will be a top.
That's a discussion. Okay.
Yeah, he's next.
In a, say, a full depth sector.
AC over some
12 inches of hot mix on a subgrade.
Subgrade.
If you use most all of the deflection accumulates in the subgrade, a lot of it, there's probably over half of it. If you assume it's non-stress dependent, linear elastic, how does that impact your approach?
In that particular case, I don't think it's a wise idea to assume linear elastic for subgrade because you have a full depth pavement. You should be using the nonlinearity,
which is a stress dependent. What I would do in that case is I would sublayer the subgrade to multiple smaller layers, and each one would have a different module. So we can back out the different module for each subgrade. So that's how it would
For most of your examples, you assume the constant subgrade module.
In this case, yeah, we haven't looked into subgrade much. So just theoretically, we haven't looked at subgrade modules. We always we do a sublayering and multiple sublayering the subgrade, and look at the whatever we know about how it changes in the subgrade, and assume linear elastic for subgrades. We are focusing on the nonlinearity of the base and the viscoelasticity of the asphalt layer. We only focus those.
Would there be an impact of the stress dependence, say a stress softening subgrade, using what you're doing now plus the stress softening subgrade? Would you care to forecast how?
If I would forecast, it should make a big difference, and it should make things very complicated, because now you have calculated.
I agree with the complicated thing.
Yeah, so
Sure.
it really complicated a lot more. So we went really well beyond of what the original task was. The original task was, well, not just because of us, Siva too. So he was very interested in nonlinearity. So original task was, okay, can we just get the viscoelastic properties somehow? Not everything, but dynamic modulus. That was the whole idea. So then we moved into nonlinearity and all that, but we have not done what you said. Here's another opportunity for the folks. To work on.
Better hurry up, I'm 80 years old. I don't receive a lot of money here.
I don't think certain things may not solve everything in our lifetime. Future generations hopefully will solve it. Yes.
I have a question
Sorry,
about.
I skipped you, but go ahead.
Uh,
Raise his hand last
My question. First, thank you very much. It's a nice presentation. A question about that sublayering you mentioned. So classical linear elastic calculation usually says when the AC layer is 2 inch or less, it's very difficult to separate them. Or it has to be more than 2 inch to see the difference between the sublayers. Do you think here also it would affect linear elastic?
algorithm itself, or
No, but the
back
result we get from the back calculation, we cannot see much difference. For example, if our sublayer is 1 inch or 1.5, less than 2 inch. Do you think in this case, is there any concern, like we should stick within 2 inch, 3 inch sublayers in the AC layer?
The algorithm that we have, if you have a half an inch, the forward algorithm works just fine. Very good. No problem. There are problems, so it has been working pretty well. So the back calculation is all about optimization. So it's not the layer elastic. If the forward works, the back calculation is the genetic algorithm or simplex. That's so your question is more related to really whether the simplex or genetic algorithm will be able to capture that level of detail. I don't know the answer. I haven't tried, but I can tell you that the forward algorithm works very well with at least 15-20 layers, half an inch, some layers, no problem. So the forward is really powerful. That is a key too. Like Julia doesn't work very well. And circuiting getting close, it actually skips. So in order to make it fast, I don't want to get too technical here, but the vessel functions are like the number of R's there, they use it very, so Julia has some problems there. So Chevron, which is a layer elastic, works beautifully. Actually, Chevron X, not Chevron X doesn't work. It doesn't have more than 4 or 5 layers. Chevrolet 2, which modcom is based on Chevrolet 2, that also works very well. Multiple, up to 15 layers, and accuracy is pretty good. But only modcom uses Chevrolet 2, right? And nowadays, I don't know, these software
Just one last question.
Yeah, it's a very nice presentation. So, I have one question. You mentioned you need to increase the pulse duration so that it uses more of the unit response. But I think even if the pulse is zero duration, it's still using the full spectrum of that response. Because if you look at the convolution equation, it still uses spectrum.
So if you look at this, so convolution equation is from 0 to t. So if you look at this, it's from 0 to t. So if your pulse duration is like 0, you're using from 0 to 0.
Not using the whole. We can consider it as zero outside of that.
So yeah, let's not say 0. Then let's say your pulse duration is 0.01 time. That's up until you don't have any more data. So duration is from 0 to 0.01. So in order for the convolution, you have to start from 0 and you only go up until 0.01. We're not using anything else.
Yeah, but you can consider other places to be zero bounded, like outside of 0 to 0.1. Like other places are zero.
Oh, I see. So like pulse and then 0, 0?
Yeah.
Oh, that's fine. As long as you have the deflection in those terms. Oh, I see your very good example. Yeah. So, okay. So let me back up a little bit. I don't mean the pulse duration. I mean the deflection history duration. So you can have a short pulse and then 0, 0, 0. That's fine. That's a very good example. You can have 0, 0, 0, 0 there, but then you're going to have deflection. Your deflection will be relaxing. It won't be going with 0. As long as you have that, your convolution is going to take care of it. Yes, absolutely right. So when I say pulse duration, I really mean, I'm glad you clarified that. So that's a very good clarification. It clearly shows you understand. That's good.
It's very similar to my study, actually.
Oh, very good. Yes? So you see, you're absolutely right. This duration is not what I'm talking about. I'm talking about this duration. So the whole duration of the time history, reflection time history. Good. Thank you. What's your name again?
I'm Shen.
Shen. Okay. Thank you, Shen.
Let's thank Dr.